Hey guys, nice to have you here. I guess we can start. So you're going to spend the next hour something with me, learning about the car parks. My name is Wojciech. I'm from Poland and I'm a researcher. I'll introduce myself in a minute. I was told to try to interact with you, but I've expected there will be alcohol here. It's not here, so I'm not sure how to accomplish this goal. But let's try it. Few words about myself. I get paid to set stuff on fire, so that's quite a nice career choice. Always love to burn things. Mother told me it's gonna end up badly. It ended up quite well. So yeah, that's quite a nice career path. I have not been arrested yet for it, and I hope to not be, at least not in the next 10 years, let's say. Um, we in the ITB, in the Building Research Institute, we are researching fire safety of buildings, and my group specializes, outside of arson of course, specializes in computational fluid modeling of stuff, buildings, car parks, tunnels. Generally we deal mostly with transport infrastructure, not because we like it, but it pays well, so it's a nice job. I also do a lot of research on all the sexy topics, facades, timber, batteries, like whatever's exciting it, and at some point reaches us, and we're invited to deal with that for somebody, and we're very happy to do so. I became a professor in the institute a few years ago. I've received some medals, boring stuff. Okay, so I like car parks a lot, outside of the fact they pay good. There are some interesting aspects of car parks. If you think about the car park, they all look the same. They all have the same role, more or less it's the same thing, copied, pasted over every building. So you could expect the fire behavior of or the challenges related to fire in car parks would be something universal. But it's not. Car parks are really exciting because very tiny, unique features of each car park make the challenges within it very unique. The fact that you, in one car park, you have entrance on this wall, on the other one you have it here. You may have two entrances, the way how the core of the building is positioned in the middle, at the wall. Is it rectangular? Is it square? How tall it is? What type of structure underneath the roof is? Are there any changes in the shape of the roof? These all seemingly tiny details make the whole thing completely different in every car park. So in the end, you are dealing with the space that's actually quite complex, and out of this complexity you have to deal with the complexity of fires within. The second thing about car parks, which is kind of difficult, if you think the role the car park has is for the vehicles to be there, and vehicles emit fumes, you don't want to be in an environment which is contaminated by the fumes from the vehicles, so they, in essence, must be well ventilated. So in essence, we have created a perfect space where you have a confined space which is extremely well ventilated. If I was a fire, I would choose this space to live in because it's perfect for a fire. So the exact things that make car parks good for the purpose they need to serve are the exact same things that make it great for the fire to grow in. And you could have a thought that, okay, we can seal down the car park and the fire will oxygen starve. I've done some calculations, and from them I've received an outcome that in a 1500 square meter car park, which is moderate sized car park, 3 meters tall, you already have enough oxygen to completely burn 2 vehicles down. So that's not a choice. It's not possible to oxygen starve a whole, well, if you have 100 vehicles burning, then yeah, sure, you can oxygen starve, though it's not your biggest issue at that point to oxygen starve it, but what to do with the building above it. So they have unique challenges and challenges that you need to overcome some way. And the last thing, no, the second last thing, they are a place of constant innovation. There is so much innovation happening in car parks, it's unbelievable. Stacking devices. You have stacking devices in Netherlands, in Poland is a cancer everywhere. Like one car was not bad enough, so let's put 3 above each other and have them underneath a residential building. That's crazy. Electric vehicles, charging points, autonomous vehicles will be interesting. The utility of the building, you know, I mean, it was already bad when I had passenger vehicles in my car park, but when they come in with a garbage truck, that's kind of scary to me, and they want to do it every now and then. So this environment is changing and evolving. And last thing, and maybe the most important one, these are not spaces in which you can ignore the risk of the fire. Fire is not that very rare event in a car park. Depends on the location. You could expect once every 25, 30 years, more or less. I think in the last calculations we done for the Warsaw region, the probability, the daily probability was like 1 to -5. So that's not, it's not something you can forget about. A fire in a car park probably in its life will happen. And we have this built as a part of bigger structures. They're under residential buildings, they're under shopping malls, they're near sports arenas, connected. So the risk from the car park in a way transfers to the risk of other buildings in its surroundings and on top of it. And when we were presenting this, because I'm rambling about car parks for like 12 years now, and people were very annoyed with me doing that in Poland, so I stopped doing that in Poland and went outside. But when I was doing that in Poland, I was always facing, but car park fires are not an issue. There was no significant car park fires in like 20 years. 2 people died, one of which committed suicide, so that's not a problem. Well, it is a problem. We had Liverpool, with a major fire that occurred when an event was happening in the sports arena next door. Imagine this happening when all of the people would be in their cars trying to go out. That would be insane. Moscow, this one we don't mind now. Cork fire in Ireland, shopping mall. Destruction of the car park led to closure and destruction of the shopping mall. 100 shops closed, major disaster for the local community. Stavanger, Norway, big car park near airport, massive economic loss because of hundreds of cars burned. And in Norway they have nicer cars than in Poland, so much more losses there. And we also had one in Warsaw 2 years ago. It was underneath a large residential building. People, it happened at 5 a.m. in the morning. They've evacuated the building, and people came back to that building like 2 months ago. They left the building 2 years ago, and for 2 years they were in the hotels in other rooms because it was not possible to go back. The destruction of the structure of the building was so profound. It's actually a miracle. They've managed to secure it and refurbish to the point where it's structurally sound and it can be used. And this was a huge demonstration of how stupid fire engineering can be. In Poland, there was a law that if you have 1,500 square meters car park, you need fire alarm and ventilation. Guess what was the area of this one? 1499, of course. So yeah, but it's now we have a proof that, unfortunately, we have a proof that this risk is not something you can go around. It is a true risk factor in your building, and you really don't want to have this fire to grow to a size where it endangers the building. So that's why we spend our time researching and learning about these things. So from my perspective, what you can do in a car park, probably the best thing is to put sprinklers in it, and that basically solves most of the issues. But in countries like in Poland, it would not be a very popular decision because we're not a sprinkler cultural country. It's not that popular, and it's increased cost over other things. So people would like to cost-benefit analysis in their buildings and then just put the things that are really necessary to. So we mostly work with smoke control. We mostly work with ventilation of smoke and heat from the building, and this is our tool, the main tool in our toolbox to handle that. And to give you some context for the rest of the talk, in our nomenclature, we would consider two major types of systems. I guess it's the same in here. One type would be like smoke extraction system with ducts, where you would have ducts underneath your car park. You would extract the smoke and fumes through openings, louvers in that duct. You would submit makeup air somewhere in the car park, and you would expect that two layers will form in the car park, one being the smoke underneath the ceiling of the car park, from which the smoke is extracted, and the smoke-free zone at the bottom of the car park, hopefully high enough to allow for safe evacuation or operational procedures of the firefighters. The main challenge with the systems would be to not mix them. That's actually the number one challenge when you design these types of systems, to provide the inlet air with low enough velocity to not create mixing effect between the cold air, because then you receive a cold smoke which will be everywhere, and you lose all the benefits of keeping the smoke underneath the ceiling. So that would be the one type of system that would be used in Poland, and I would say it's like 40% of the market in Poland. The other one would be jet fan systems, and that would be, I would guess, 60% of our market. Most of the car parks are equipped with jet fan systems. It was brought to us by Dutch people, Novenco, who did the first system in Poland in, I think, 2002. It was a nice revolution. Back then, the ducts costed a fortune, so ductless systems were a really nice thing, and they really gained a lot of traction on the Polish market. The issues were, I'm telling you that to build the context on our research. The issue was that suddenly there opened a large market for these types of systems, and companies started competing who can design the smallest system for the building to win the contract. So we very quickly went from the large Novenco systems with 500,000 cubic meters per hour extract points to systems with 300, 250, 200, who can give less. It was going less and less and less, and then we as the ITB, we went out and say, no guys, stop. It cannot, like, if we go that, we'll go to like sanitary mode systems, not fire alarms, not fire systems anymore. We've proposed some guidelines in Poland. We're showing people how to do CFD. We've gained them preliminary designs. They wanted to kill us for that because it was against the competitive advantages of some people, but we did it, and it kind of worked. So we've stopped in Poland at the low capacity systems at around 180,000 cubic meters, which we call smoke clearance systems, which I will show soon, and we still have some proper jet fan systems in the car parks. So that's pretty much the systems. The difference in their operation is, as on the picture above, it's the same car park cut at 2 meters height. After some time in the duct system, you get a stable layer of smoke. You assume that as much of smoke as you produce, this is the amount you remove from the building, and by that you receive a status quo where your system just continuously works at a certain efficiency, and you would expect it's not going to change much over the course of the fire. In jet fan systems, we usually allow the smoke to gather in the smoke reservoir of the car park to not disturb it too early, because that, from our experience, gives a better chance for people to escape. Instead of pushing the smoke on top of them, it's easier to leave the smoke to spread for a few minutes. We've obviously checked that with CFD to see how long that time can be and what's safe in a given architecture. And after some point, the jet fans start, the exhaust starts, and you start carrying the system from the inlet side to outlet side, basically removing it horizontally through your car park. Obviously, the efficiency of the system will be driven by the system capacity and the size of the fire. That was the second thing that was very disturbing in Poland. When they ran out of the possibilities to optimize on capacities, like directly, they started optimizing the fire source. Yeah, one guy did CFD for 4 megawatts, the other did for 1. Guess which system was better? So yeah, it was also a very huge pain for us that required fixing, and we did fix it in a way. Now, before I go into my talk, I'm going to show you the results of our modeling, our research on this subject. but it's not complete. It never will be complete because of the reasons I told you about at the beginning. It's always a very unique thing for each car park. And I'm a huge advocate for designing smoke control systems in car parks through CFD. It's annoying, it's costly, but it's necessary. There's no way you can. There's no way you can, unless you over design. Like if you put 500,000 cubic meters per hour, then you're okay without CFD. But that's the Belgian way, which we don't like here, as I was told. So, which means it's basically a French way. So that's even worse. So you need to do CFD for car parks if you want to have optimized and working systems, and I'm a huge advocate of doing that well. We have some publications, we have done some preliminary work that I'm not going to really cover that much in here regarding the jet fence performance, regarding do you need obstacles or do you need to not model obstacles in your car park? That was also always a stupid question we've been asked 100 times, so we eventually did a CFD analysis Monte Carlo to show that the obstacles in your car park don't really have a big impact on the qualitative outcome of your analysis, which was a really great thing. If we found otherwise, we would not publish it. So we're happy with that. And let's jump into the subject of today. What matters when you ventilate the car park? We've started doing that, asking that question and finding answers, seeking answers around 2017, where we've did the first parametric study. We wanted to see if we have a car in a car park, actually in the two different car parks, one is narrow, other is wide, and the heat release of that car park is set at different levels from 1 megawatt to, like, I think 16 megawatts was the biggest heat release rate we've modeled. And we have a system in this car park based on jet fence extraction inlet, here the same, extraction jet fence inlet. If we have a very most simple jet fence system that you can have, how will the performance of that system change as you change the operational points of the system? You increase the capacity, and how will it change when you change the power of the fire source? So will the system still work if the fire is twice bigger? That was a really tough question to answer because we had no idea back then. And we very quickly observed these fundamental differences between different quality or different size of the systems. As I mentioned, we've started calling them clearance systems and smoke control systems in Poland as a sort of nomenclature that we've introduced our engineers to. The clearance systems were meant to remove as much heat and smoke from the car park as possible to allow firefighters operation inside in a way, assisting. They're not enabling them, but assisting the operations, while the smoke control system was supposed to create conditions in which all of the smoke is behind the fire source. So you enter the car park in a smoke-free flow, and you can get to the car park to the car on the fire and extinguish it. So that was the objective of control. And this is a good illustration showing that. It's a smoke concentration, red is bad, where for the same fire, 9.6 megawatt, that's the peak fire from the TNO curve, the Jean-Baptiste Schleich curve that I think is popular in here as well. We also adopted it in Poland. For this size of the fire system with 45 cubic meters per second, in this particular car park, has not succeeded really well in removing the smoke from the system, because the smoke has moved almost 100 meters up the car park. So almost the whole car park is filled with smoke, while a system that's 40% bigger has successfully stopped the smoke more or less at where the fire is located. So that's the most direct difference between the performance of clearance and control. However, this picture does not give you all information, because the smoke, in terms of the substance emitted by the fire, the soot and conglomerates, it has very nasty optical characteristics. It takes very little of this substance to obscure the visibility. Actually, Um, I show you smoke concentrations of 0 to 0.2 grams per cubic meter, because this is where this visibility that's relevant to humans is. But in car park fire, we can go to concentrations of 2.5, much bigger than this. It actually takes very, very little smoke to obscure the visibility. So it's a parameter that rapidly drops to 0 or close to 0, and you lose your ability to investigate which is worse, like which part of this red is worse than the other. If you look at temperature, you see more. And here, you can see that the smoke clearance system, despite the fact the whole car park is filled with smoke, this smoke in here is not a very hot smoke. It's something we would call a cool smoke. It's around 120 degrees. It's not, of course, not fun to walk in it, but it's something that a fully equipped firefighter could possibly handle. Of course, it will have an effect of disorientation, and it will be very difficult to find the source of the fire. But it's not. It's something that lies within your operational range that you can equip with personal protection devices, go in and sustain. So this system, despite the fact it doesn't stop the smoke, it actually really does well in containing the heat. So that was for us very important, because not every building has to provide these conditions. Sometimes this is sufficient to okay a building, especially a residential building, where the costs of going from this to this would be tremendous. We have, obviously, I said this multiparametric analysis, so we've investigated it with many points of operation of the systems, increasing the capacity, increasing the fires, to really look for that signature when clearance becomes control, when control stops being control and is just a clearance system. So here's a comparison of the performance of the same system at different capacity points, from 45 cubic meters to 77 cubic meters per second at a 4 megawatt fire, which according to British nomenclature would correspond to a sprinklered car park. That's usually it. You know where the 4 megawatts came from? Howard Morgan once said it's going to be okay, and it's okay now. That's how we're still using it. So it's kind of funny when you start digging off for the fundamentals of our discipline, because you may not be happy with what you find. In here you can see that increasing the capacity of the system obviously leads to improved performance. However, the improvement between this point and this point is almost none, because they pretty much achieve the same goal. I would even say that this one is already okay and this one is, let's say, questionable. But obviously by increasing the heat release rate, by increasing the capacity, you will obtain a better system. But now the good question is, I know that I designed a 4 megawatt design fire for my car park, but do car parks in the car park do not exceed that value, and they usually not behave like we would like to. So the good question was, what will happen if the fire is different? And that was something we've took a look at, because if in the same car park I put 8 megawatt fire, suddenly my system that was at the edge of being controlled, this is not really fulfilling our criteria for smoke control. This one is. It stops being smoke control. More of this car park is filled with smoke. But it's not that we've lost the capability to control the smoke in the area. It's not that we've lost capability to control the temperature and energy balance in that area. It's just a bit worse. And the bigger the system were, the lesser effects of this increase. So not only you are increasing the performance of your system at some given stage, but you're also increasing the resiliency against the bigger unforeseen design scenarios. We thought that it's a good finding, but designers thought otherwise. They want to design for the minimum. Anyway, it's also interesting because when you venture into bigger car parks, wider car parks, this one is perfect for jet span systems. It's narrow. If you go to bigger car parks, to stop smoke in here, you would need to create a certain amount of flow, certain flow velocity even, that is big enough to countermeasure the forces in the smoke, the buoyant force of the smoke that wants it to move this way. So there's like a balance of two forces in this point, and you want to overwhelm the smoke, then you can control it. If you don't, you get this. So obviously, if you have a fixed point in your system, you extract 50 meters per second in your system, subdivide that by the area of this, and you have more or less the average velocity in this space. Must be high enough. Now, if you wanted to design for this velocity, you would get up to a really, really huge values of extraction capacity, because even 2 meters per second on such a huge area, it's unbelievably large systems. It's something we would do in tunnels, not in car parks. And as you build your car park, as it grows, you can really see that effect, that something that has worked, remember 4 megawatts in a narrow car park, up to, well, this one horrible, this was okay-ish, this were perfect. Here, the performance is completely different, the same capacity. So it's, we did this to show to people who focus so much on capacity, and they were designing systems for capacity point. They were calculating, okay, in this car park, in every car park we need 200 cubic meters, 200,000 per hour, and it's good. No, it will depend on the car park. In one it will be great, in one it will be horrible. So we wanted to show them that this performance will be completely different once you start making the car park bigger. And it was. As you can see on this picture, this performance is completely different than one observed in the narrow car park. And if you go to larger firepower, it's even worse. But still, some of this performance was acceptable. The next thing that we wanted to see with this preliminary research was the effect of jet fans. People highly misunderstand the purpose of jet fans in jet fan systems. Jet fan is not the device that is hanging above my head and transports smoke from here to there. It's not the device that acts just in front of it. It's something that acts like 30 meters from me, where the stream of the jet fan is big enough to cover the whole space of the car park. This is why you see these beautiful shapes on my simulation. This jet fan makes its effect here. The jet fans that are somewhere here make their effect here. It takes distance for the stream to spread, and then it starts to make sense. It's like if you wanted to blow leaves from the ground with a leaf blower or a straw. If you push a lot in a very small space, you're not going to move things. So jet fans move at a distance. They move air at a distance, and their main role is to make this movement as uniform in space as possible. Now, an obvious thing for some of the designers was to optimize the systems. And what is the number one most expensive element of smoke control system? It's the space of the floors you're taking for your ducts. If you need a 5 square meter duct through 10 floors, that's 50 square meters lost that could be sold otherwise. That's the biggest cost. And people really hate optimizing for larger cubic capacities of their smoke control shafts. They would rather find solutions elsewhere. And many of our colleagues, designers, were trying to optimize by putting more jet fans in the system. So, okay, if we have this bad smoke behavior in this place, let's put a shitload of jet fans in this location, and it's going to be great. They're going to blow it away. Well, no, it doesn't work like that. So, what is a jet fan? Jet fan is a momentum transfer device. It transfers momentum from the blades to the air. It just pushes the smoke, transfers a force. If you don't have any jet fans in your car park systems, here is at the 55 cubic meters per second. You've seen this image before on, it's this car park, this simulation. If you don't have any jet fans in the system, at a very large fire, I told you you want to balance the forces. But if the force of the smoke is too large and this one is too small, they don't want to battle, they just go one under another. So you will have a lot of smoke coming back from the top of the car park and your cold air flying underneath. There's no reason why. That's the path of the least resistance. So you will see that your smoke moves up all the way it can. If you start introducing jet fans, and here we've introduced 15, 30 Newton jet fans, which are a little tiny, you already see a significant improvement from 0.0, because you suddenly uniformize the flow in your space, so the smoke is going where you want it to go. At 50 Newton jet fans, you probably reach some pinnacle of the performance of this particular system because you're more or less controlling the smoke in half of the car park. For the conditions in this picture and the size of the system, it's not a bad outcome. Now, what would happen if you put more jet fans there? You start to overwhelm the amount of air that you extract. It cannot take all the momentum you've transferred into the air in your car park, and that flow has to go somewhere. In this case, it went around this wall, moved all the way back, and created this very unfortunate pattern of smoke, flowing backwards despite you blowing more on it. 100 Newton jet fans, it's even worse. By doubling the size of the jet fans, we've made the system double worse. So there exists a balance that you need to find, and that is another reason for doing CFD in your calculation, because there is no really good way to calculate that on a piece of paper. I know some ways, they're very unreliable, CFD shows otherwise. So there's no really good way to do that. But it's necessary. Otherwise, you're going to overwhelm the system in the car park, and it's not going to do the thing that you want it to do, which is removing smoke. And let me show you a practical problem. We were designing a large car park underneath the shopping mall with the jet fan systems, and because we wanted to subdivide it into smoke zones, we ended up with this funky smoke zone with 3 open edges. So we were super smart. Let's cover it with jet fans all around, and we did. And what it did to the system, instead of smoke going to the extraction point, it was going everywhere. Because you cannot overwhelm the system with the amount of jet fans. When we used less jet fans, when we turned these jet fans off, it worked. You just had to really control at which location, which jet fans you start. But it's not possible to simply throw a bunch of jet fans and it's going to work. It's not going to work like that. So that was the initial project in 2017, in which we, for the first time, really touched the subject of what matters in the system. But it was very interesting. It left us with more questions than answers, so we pursued it further. We moved on into a second project, in which we have designed a car park, 40 by 60 meters, quite large car park with a fire in the middle of it. We've designed it with ductwork systems and jet fan systems, and we did CFD the hell out of it. We have performed, if I'm not wrong, 480 different CFD simulations for this car park at different setups to really understand how different variables change the outcome of our modeling. From some interesting facts, it took us 78,000 hours. Actually, it took like twice, but I cannot tell that to my boss because he's gonna kill me. We've started like 200 simulations and forgot to start the fire in them. Yeah, that happens more often than you would like. In this project, we have varied stuff related to architecture, stuff related to fire, stuff related to smoke control. From the architectural one, we have chosen the height of the car park as the variable we want to look at. So we've had horribly low car parks, 2.4 meter to 7, 3, 3, 3, and 3.6 meter. So we've repeated the calculations for each of these heights. From the design fires, we've used Jean-Baptiste Schleich fire, we've used alpha T squared fire, we use rapid fires. You're going to see about that later in the talk. So we took the famous TNO curve that everyone likes and enjoys. That was our fundamental source of fire. But we will focus on modeling like this early part of the curve in relation to the growth of the fire. So if we want to investigate the consequences towards the evacuation, we were modeling the beginning of the curve. We skipped the part that's boring, and we went into steady state fires that correspond to 1.4, 4, and 8 megawatts as some sort of steady state fires to understand the conditions in the building when the firefighters would come at some point. So that were the fires. And for the systems, we've again investigated, well, now we've investigated duct systems and jet fan systems at different points of operation. We had a car park where there was no exhaust, it was just an open wall, so you could blow all the way through it. And that was a lot of systems, and it was very interesting. The amount of variables and changes in the model to be implemented in this project was so overwhelming, we had to resort to coding to actually do the simulations. So we wrote in Python a preprocessor for our simulations, which would build the FDS models for us. And that helped us carry these hundreds of simulations. So we built the geometry, we built the preprocessor, and we told him we want this combination of variables, pressed enter, and it popped out 480 scenarios to be simulated on the computer. Obviously, it was quite a lot of work, but in the end, it was better than writing 480 cases in FDS, which would probably kill me if I had. I'm dying after 3. So that was very helpful. And the same thing was for post-processing. So to go through the results, if I just wanted to open every of them and watch for 10 minutes in smoke view, it would be in general something like 2.5 days of looking on the smoke view, which I'm also not the biggest fan of. So we had robots do that for us. We have received every single possible outcome. That was quite funny to plot them on one plot. So yeah, the not very meaningful plot, but very colorful one, and I like it a lot. Literally every single possible outcome, from the absolutely smoke-filled car park to a car park that's pretty much free of smoke and very good to be used. So we've covered the whole spectrum of performance of different fire systems. We have observed large variability in the results. Here, for example, you have a small fire of 1.4 megawatts at the very low car park, and we have received a plethora of results for this single case, from jet fan systems at very high capacity that basically cleared all the way through the car park because of the low heat release rate and huge cubic capacity, to duct systems which are not very different from no ventilation at all. So we have received really a lot of different outcomes from our modeling, which made us really happy, because that meant there are variables that differentiate why this looks different than this one, from systems that are perfect to systems that call for Batman for some reason. Obviously, as the heat release rate grows, as the fires get bigger, the differences were less visible. So we've also identified at some point the moment when the system stopped work, to identify when they really lose the performance. We really like to show the results in this way, which people find super confusing and no one understands, and I always also struggle. But if you cut a slice through your car park and just plot it second by second on one plot, you get to see the time evolution in the space on a two-dimensional plot that you can print, because they want us to put this in scientific papers, but you cannot really put an animation in the paper, so we had to figure it out. So if you look at the car parks with a very low ceiling, and on these plots, which are time-space again, I've marked the lines which would be from 3 to 5 minutes, which from my experience would be the evacuation time of the car park, depending on what pre-evacuation time distributions you would choose. So the 3 to 5 minutes is something that we feel comfortable with as the evacuation time of a car park. So red means there's smoke in the car park everywhere. And with jet fan systems, in which we purposely delay the initiation of the system, it's obvious you're going to have a smoke in your underneath your ceiling for a good time, no matter the size of the system. In here, the extraction points were working, it's just the jet fans were not working, and then when we start the jet fans, it's related to our beautiful law, which forces us to do that. In ductwork systems, even the high capacity ones, they could not save the car park. It was filling with smoke very quickly. Actually, in a way, as a paradox, without ventilation, it was even a little better than with very powerful ventilation, because of the disturbance this creates. So, in a very low car park, we have obtained very bad results in terms of capability of people to escape this car park. In every of these cases, most of the car park is red, which means it's filled with smoke in the time in which you would like to escape. So definitely a very bad outcome of a fire. Now, if you start combining that with changing the height of the car park, some really interesting stuff begins to show. Even at the very low capacity system, 17 cubic meter, that's a very small system. But with the growing height of the car park, you start to receive some pretty good outcomes. Whereas in the smallest car park, after 90 seconds, you already would be in a smoke. Here, at 270, this is only at the edges, at the walls of the car park where there's recirculation. But most of the car park is smoke-free. At 3 meters, it's almost completely free in the evacuation phase outside of these really tiny spaces. At 330, completely free. 360, completely free. So by simply changing the height of the car park, it's not a simple change, I know, but you can see how completely different the performance of the system is with this change. And one interesting thing about this, it's all for the same cubic capacity, 17 cubic meters per second. If you go to design, how we design these things, you would calculate the amount of smoke in your smoke plume and assume that that's the amount you need to extract. You would usually assume that your smoke-free layer is at 80% height of your car park on some other artificial value. So if you make the car park taller and taller, you get a bigger entrainment, so you would have to design a bigger smoke control systems. So in a way, you're penalized for making a bigger car park because you need a bigger system to match it. Well, bullshit. If your car park is higher, your system becomes more and more efficient because the size of the smoke reservoir is bigger and it's easier to extract smoke from it. So that, what, Andrea?
At which height is that smoke?
This is plot at either 1.8 or 2 meters. I think it's at 2 meters, which also makes sense because if you have 2.4 meter car park and you measure at 2 meters, the smoke layer will be at 1.5 meters. But we design car parks for people can walk out, not crawl out of them. So that's the point. Yeah.
Is it standard in Poland to design these kind of systems for evacuation purposes?
Yes.
Yeah? Because at home we typically don't do that. It's not our.
Yeah, but we care about people. I'm sorry. It is common to design this. Technically, we have a performance-based law that says smoke control systems should be dimensioned in a way that it's sufficient for humans to evacuate from the building and sufficient amount of makeup air is being put in. So evacuation is directly within our goals, and we care about that. I agree that depends on the type of your building. If it's on the residential building and you have 3 people in a car park, it probably doesn't make sense. If you have it's underneath a shopping mall and it's Black Friday, it probably does make sense because you may have 1,000 people in there. So it's all contextualized, which also we fail to have in Poland, and we cannot now, because they kicked us out, we cannot participate in the discussion. They don't like us. But yeah, it is sometimes irrelevant. However, I still find it interesting that you can improve life safety by increasing the height. And even if you don't care about it as your primary objective, it's great to know. In jet fan systems, we obviously observe the exact same thing, increasing the car park height. We also observe the increase in performance of the system. Now, the interesting thing in here, I also told you about this balance of forces and the amount of air you have to push through the car park to achieve it, which is related to the square area of your cross-section. So the higher the car park, the bigger the cross-section, the bigger the velocity, right? Well, again, in here we've observed that the amount of energy in the smoke, because of its lower temperature, because of its increased entrainment, makes the buoyant forces so much smaller that actually system becomes more efficient. It has lower and lower average velocity, but less and less is needed. So it's not that you need to increase the capacity multiple times, because if you increase the height from 240 to 360, you still achieve a better performance of the system. So from our perspective, that was a very important finding. If you combine them all, which you probably cannot see the green ones at least, they're here, the points. That's the mean visibility in a car park after 7 minutes of the full size fires of 140 and 8 megawatts. And in here, if you could see it, you would see the difference between the systems. And the most interesting finding in here is the fact that with the lowest car park height, you can barely distinguish the points on the plot. Here it's almost, they're all clumped in one space. Here, they're scattered. What this means? It means that if your car park is not high enough, you can barely tell the difference between the systems. You cannot put much larger system and hope it will work, because it will not. You cannot overcome the limitations in the size of your smoke reservoir with just the capacity of the system. You only start to see the differences when the car park is tall enough. And that was something that we have consistently observed in this study, that only once you started implementing a certain height of your car park, you started to achieve good performance of the systems, and then you could truly engineer the system to the certain space. This study was very important for us because as fellow engineers who design smaller and smaller ventilation systems, we would have fellow architects who would design lower and lower car parks as low as possible. And we wanted to show them, no, there is a safety limit. You really, if you want this car park to be a part of a larger building complex, please make it at least 3 meters tall, because then we can work with it. Then that is the point where we can actually provide safety. So that was interesting aspect of this study. But in the meantime, there was another thing happening. A fire in Shanghai, where a nice white vehicle has quite quickly ignited. And observing media, observing images from the world, we've realized that electric vehicles are burning in a slightly different manner than everything we know. And I don't know about you, but seeing this growth of the fire scares the hell out of me as a designer, because my design is not that design. That is not my design. That's not my design fire. I don't know what that is, and I don't like it, but it's not my design fire. And I'm responsible for my car park that I've designed based on my design fire, because I told people this is a design fire that is representative for the threats in your car park, and they believed me, and this is not the thing. So we started to wonder, so how much worse this thing is compared to design fires that we commonly use. How does this differ in the outcomes compared to these fires, and can we actually do something about it? Because let's play we're fire systems in this car park. So the fire is growing. You're a detection system. No, not yet. No. Maybe first beep now. Someone deleted it. Second beep. Second sensor. And this thing is already huge. You want to start your smoke control? Okay, let's close the dampers on the sanitary modes 1 minute from now. Okay, let's open the dampers. Okay, let's start the fan now. 3-4 minutes into the fire, where this car is already in inferno. So it's not that our systems can really react quick enough for this. So we're really intrigued in how this changes the environment around us. Because people came to me and asked me, Wojciech, do we need to design car parks for electric vehicles now? And I told them, well, unfortunately, we've been doing that for 30 years. We just didn't know about it. Because it's not that we can stop people from entering car parks with electric vehicles. We tried to do that with LPG vehicles in Poland, and yeah, they don't really work, telling people to not enter the car park. They kind of ignore it. But to be quite honest with you, these are not the only fires that can grow this rapidly. There were experiments at RISE where combustion vehicle has burned even quicker than electric vehicle. It has to deal with the fact they've put fire directly underneath the fuel tank, so it could have been expected. But still, there are scenarios in which our vehicles can burn as fiercely as these ones. So obviously, these curves then make sense for electric vehicles because the way how this starts is completely different. Our idea was, okay, we have no idea what's the size of this. We have no idea how quickly it develops from the moment it goes into thermal runaway into full fire. We have no idea of what the jet flame dynamics are, jet flame dynamics are in this case. The best we can do is just simulate a very quick fire. Like take our normal fire and just make it grow super quickly to, in a way, represent this immediate threat that this introduces to your car park. And this is how we've built 6 different heat release rate curves for the purpose of the experiment. Because at that point we had no idea what the heat release of that jet flame will be, and we still do not have a good idea yet. People are working on that, but no answers yet. We've designed curves 250, 500, 750, and so on kilowatts that grow to the full fire in like 30 seconds, so it's almost vertical growth of the fire. And the fun thing is that 750 in terms of total energy generated matches the 3 minutes of TNO, and the 500 matches the, 750 matches 240 seconds of TNO, and this one matches the 3 minutes. So you can put, in 3 minutes they would emit the same exact amount of heat and smoke in the car park. It's just the one does it very quickly and flattens out, the other grows. So we've put those curves into our simulations to see how they go, and this is the result for 2.7 meter tall car park. On the left you can see the 750 kilowatt fire that immediately grows. Here's the alpha T squared, and here's TNO, and you can immediately see that this one, more quickly than the others, overcomes the car park with the smoke, and the smoke is produced much quicker than in other cases. In fact, if you look at all of them together, you can see that previously for 270 meter car park, we would have more or less this outcome in a normal design fire. Here it can be much worse if the fire is growing to a much bigger number. What does it mean at this point? We don't know, because we don't know which of these heat release rates these cars have. From what I've been told by people from Sheffield and other universities that investigate, they are at the numbers between 750 to 1250. So somewhere in the middle of my graph, we basically more or less got it, but it's not a finite answer. But these things overwhelm the system quicker. Here's an animation that shows that, and in this animation, it's like one simulation subdivided from another. So if the color is blue, it means that it was worse in the classical design scenario. If it's red, it means that the fast fire was worse. So the 250 kilowatt is mostly blue, so it's much less smoke, and the current design fire is much more onerous. These guys are almost white, which means there's not that much difference between the current paradigm and the new one. And these guys are mostly red for most of the time. So the consequences in that car park are far worse than in the normal design scenario. If you put system in it, if you put a ducted system, they do not change that much the outcomes of these fires. They are still very bad because of the reason I told you at the beginning. It's not that we can start them at 0.0. You have to give the time, and because of the ductwork, you have smaller smoke reservoir, so it's worse. So the conclusion was that if it's around 750 kilowatts, if you end up with this fire as the electric vehicle quick fire, our current approach is working well. If it's smaller, then our fires are worse. If it's bigger, our fires are not worse, and the electric vehicle fire will be much worse for the outcomes in the building. And here, we have also observed this profound effect of the height in the building. Really profound effect that increasing the height has significantly increased the capability to escape from that building with time, because it's a passive thing that is there. Smoke reservoir is there. You don't have to activate it. It's always there. So it makes sense. With larger buildings, you can have much better environment for a long time, long enough to escape. So if you build 3-meter tall car parks, you not only possibly improve your ventilation system performance, but you also allow for escape in a scenario such as the fire of electric vehicle that develops very rapidly. And here's 5 more slides about the same thing, because that's the main thing we found. The height of your car parks is the most important variable in designing the car parks and the systems in them. So yeah, that would be pretty much it from the part that I've prepared, and because it was supposed to be workshops, I would be very happy to answer the questions you may have about designing car parks. So if there are any, please go on.
I have a question. I understand it correctly that your discussion on 3 meters is it the conclusion which is more related to the required safe egress time and the available safe egress time, so for evacuation purposes, and not for firefighting purposes? Or is it the same?
It's in a way.
For firefighting?
No, conclusion is more or less the same. It's better for both because we've observed better performance of systems in taller car parks, which eventually affects the conditions for firefighters. So if you have a taller car park and your system is better at removing the smoke, the better the conditions you will have inside. So increasing the height will also improve the conditions for you guys. In Poland, the discussion was mainly towards the evacuation phase, because that's the thing in our law that we are supposed to provide. So our number one argument was, okay, you see, you have better times, you have better egress, you can have longer distances, because it translates to many parameters of the car park, like horizontal travel distance. That's a big thing in Poland, like what is the maximum path you can have to exit of your building, and if I can increase it from 40 meters in the low to like 80 meters, that changes completely the design of the car park that the developer can make, the amount of vertical routes and so on. So it's a huge, that's a huge, they would trade 30 centimeters of the car park for the ability to have 2 less escape roads in it, because we could increase the horizontal distances. Obviously, you have to look at it holistically, what would be the better for the building, but obviously no one does, and fire experts would just sign off what's the cheapest available thing possible. But here we've really shown that by changing the height is the most impactful decision you can have. For evacuations, for sure, for firefighter operations, it's also very meaningful. Maybe it does not solve the issues, because you will not create a smoke-free environment, but it certainly improves the conditions. And one more thing that it changes, which is interesting, because you will see lower, because you will see lower temperatures underneath your ceiling in your car park, the radiation will be lower. That's something that we are currently investigating, because we're now in the next stage of this endeavor. We're now simulating car parks, open car parks in wind conditions, and we want to see how the fire spreads between vehicles. And if you have lower radiation from your smoke layer, you have lesser threat that the fire will spread very quickly. And if you look at the statistics, in car park fires, you either have fires that have 1, 2, 3 vehicles, that's the usual ones, or ones that consume, I don't know, 10, 20, 30. You don't really find fires that destroyed 5, 6 vehicles, because there's a cascade effect. At some point, it just ignites next car and next car and next car. I think you guys had such a fire on Schiphol Airport, open car park, where it burned a lot of vehicles. So it was jumping from one to another, right? At some very close together. Very efficient. Congratulations.
I'm from Belgium. 500,000 square meters.
Yeah, you don't need CFD. Yeah.
No, but we had, for example, a fire at Zaventem Airport. I think maybe 8, 9 vehicles burned there.
So again, a very large fire. Yeah, and this is the type of the car park we try to investigate now, to see what really how wind, in essence, the project is about wind more than car parks, but car park is just such a nice case study for wind effects because of the way how you can describe the fire of the car and how it jumps from one to another. So it's really interesting for us. That's really interesting for us to see this dynamic and how it changes. Yeah, so that's interesting for sure. Yeah.
A couple of questions.
Yeah, go on.
First of all, thank you very much.
You're welcome.
The first question is about how these systems are activated.
Automatically.
What is their strategy? Is there connected to smoke alarms?
Yeah, in Poland they
What's the
no, in Poland they would be automatic, automatic smoke control. Automatically, there's a scenario of operation, fire in smoke detection zone. This means operation of smoke control in another zone, and I don't really see how you could do it without automatic operation and without detection systems. I know, for example, in Australia, they struggle because they don't have fire detection in car parks, and it's like really crazy to put smoke control in there because you don't really know when to activate it. So what's the point? Yeah?
On to that, you said it's smoke activated. Aren't you afraid that those systems will work too early because of the false positive?
Yeah, but that's not the problem that much. Like, even if they do, the consequences of this false positive alarm are not tremendous. Like, from my experience in a shopping mall, they sometimes can be significant because of two things. You usually would shut down the HVAC of the whole building, which is for a large shopping mall, it takes 2-3 hours to set it back up. And we had shopping malls where there's these food court areas, and usually you would cut off the gas immediately after the confirmed fire. So false alarm has quite annoying consequences for the operator. But then you design coincidence on the smoke detection sensors, so you need 2 sensors to go into stage 2 alarm. If it's just one sensor, you go into first confirm you are there, and the second thing, there's a time for the personnel to check either with cameras or walkthrough. And you can play with that time. You can make it 3-5 minutes, so they have sufficient time to check. If you're afraid, you can shorten it. But then again, if the second sensor catches the smoke, it means there's a fire in the building, so it just goes on then. So that would be the strategy we usually would employ in such a building. Andrea?
Yeah, the other aspect is, have you looked into how the flow fields inside the car park might influence the burning of the car? Because all the cars and experiments we show this, in a sort of quiescent conditions that you have just big and trainers. But what if you're using your jet fans and you're sort of blowing into your fire? Wouldn't the fire spread be faster, therefore going very similar to electric vehicle condition?
That's a good question. We have not looked into that because that would require experimental research. I know a lot was done in Flanders by Schever-Deckers, and like 2 or 3 years ago, looking into these dynamics between smoke control and sprinklers and these velocities. They've burned a lot of cars, but I haven't really seen the final reports in English, at least. So that's nobody does.
Unless
Yeah, that's
private research.
that's unfortunate. Maybe we'll be able to steal that out someday, because it's a hell of a project. It's a really interesting project. That's an interesting dynamic that could be studied and should be studied. It is not involved here because our design paradigm is the design fire. We take the TNO curve and we implement that, and we don't care if different conditions would result in a different curve, because otherwise you would be not able to design a car park. You need a design fire, unfortunately. So this type of dynamic is not possible to be included in here. In our little book that we've published for a Polish market, we have implemented a safe fuse for that. So we tell people, okay, you need to demonstrate that outside of a radius of, I remember, 5 meters from your vehicle, the radiation does not exceed 15 kilowatts per square meter. Because next to the fire you may exceed that, so you may ignite the vehicles next to you. But on a larger scale, you should not have this. This is only possible if your hot smoke layer would be very, very hot. And if you don't exceed that, it's very unlikely you will start igniting the next vehicles and next vehicles. And that you can see in the flow field also, because your smoke will be moved. But when you move smoke, you cool it tremendously, very quickly. You see that when you simulate tunnel fires. You pop 100 megawatt fire in the tunnel, and 50 meters down the tunnel, the temperature of smoke is 200 degrees because of how it turbulently mixes with the incoming air. So it would have effect on the dynamic of the growth of the fire, as you said, especially if the fire was in the passenger cabin and you would have open windows, then for sure. If it's like in a very, because cars are built to be very weather resistant, you know, for rain and everything, so it's very confined space. So if it's in the engine chamber, you don't really have this risk that much. So in this case, I don't think the impact would be that severe. And the impact behind the car, you can see it in CFD, and we have not really observed anything that would concern us very, very much with longitudinal systems. I mean, the benefits would outweigh the possible consequences and anyway. So yeah, but isn't
I fully agree. Just for me is every time we start with design fire, but we should also consider sometimes the design fire is affected
yeah
by the variable you are changing in your design.
yeah. Design fire is in a way an output of the fire. It's how the fire will grow, and I wish I had a better answer for. We are working on some mechanisms to take that into account. There was a PhD by Tohir, who did flux time product calculations, how much energy it takes to ignite parts of the car, which can be used to trigger fire start in different space. So it's a nice starting point. We don't know how the growth will be affected by this change, and producers are very reluctant to give us a bunch of cars to burn for some reason, which I would love to do to understand. But it's hard to get data. And that's another thing. It's very hard to get data for car parks. There's a reason why we are still using the results from 1999 in TNO, which was based on vehicles from 1995, I think. There's a reason, because no one has done a better study yet, so far. There were other studies, but they have limitations that make them not very useful. With studies in France, which we don't use because it's French studies. There were studies in UK, which had very small calorimeter that definitely affected the growth of the fire, and they were carried in a different way. There are massive, like a lot of people, a lot of firefighters are burning electric vehicles now, but they don't do it systematically, and they don't gather the necessary data for us to produce a design fire. So basically we see all these cars being burned here and there, and it's basically useless data, because it's very difficult to design experiments to identify a design fire. And you have to be very thoughtful about that. You have to go through event tree analysis of what led to the fire. You need to do a lot of things that allow you to generalize the conclusions of your experiment and be useful for public. It can be done, but it is very, very difficult thing to do, and most of people don't do that. There's a reason scientists are very rarely designers, and they don't really understand what designers need. Designers are not scientists. They don't know how to do experiments. And there's me, I don't have cash for that. So, yeah? He was a split second quicker.
I just have a technical question. So
Yeah.
what car occupancy are you assuming in your simulations, and what is the car height or size that you're assuming?
Yeah, so in this we just assume a typical sedan vehicle. So just a normal car, not a huge SUV, not a huge minivan or something. So their classification of cars is done. Actually, I've read the French report. It's in the French report. There is a nice classification of cars. You have to give them that. But we're gonna steal it and call it our own, and then it will be nice. So you have the classification of the size of the cars and different total energy release they can yield. So you can diversify by that value. We just don't do that. We take the Schleich curve, and it's for general cars. So it doesn't distinguish. And in terms of occupancy, we really don't care that much in terms of what's beyond the car park. The car park is car park, and in this project we didn't really care what would be above it. But obvious from the
But it will change your, you know, the dead air volume that you're going to move with your jets, right?
The car parks were empty, if I understood it well.
yeah, the car parks were empty. Ah, you meant how occupation as in the cars that were... Yeah, we did the research on that. We did the research that was published on how much the amount of the car park you fill with cars changes the outcomes of CFD. And what we've observed in that if you have simple shape car park, like a rectangular car park with no obstacles in the middle, these additional vehicles have not changed the quantitative results at all, almost. Yeah? 5 minutes? Okay. So we've done that previously. It was like 100 Monte Carlo simulations with, we had algorithm that was randomly putting random cars of random sizes in random places of the car park and repeat the same simulation 100 times. It was really fun. And it's shown that in scientific car parks, which are perfect rectangular, it doesn't matter. In real car parks, it matters to an extent. Like the more complex the car park shape, the more impactful that was. And definitely at some point, like we've even figured out the way how to distinguish if it had an impact on your simulation or not. Because if you have let me show you any picture of a car park. Yeah. So if you see a simulation and on the velocity plot you see like one giant vortex that spans through your car park, and one side of the vortex is full of smoke, one side of vortex is clean, it doesn't mean the car park works. It just means that you have a huge vortex that stopped the flow. And this usually is because you had your car park empty, because such a huge vortices cannot form in a car park that's filled with cars because the obstacles will disturb them. So if you see this kind of dynamic in your car park, it means you probably should investigate the effect of the vehicles in the car park on the performance of the system. And that's also what we've seen in that study. It's published in English. You can, if you Google me, you can probably find me on ResearchGate, or you can contact me on my email. I can send it to you.
What we've seen also in tunnels is that if you have vehicles, also the section of your, of where you're blowing air is changing.
Mm.
So if you have the same speed and a smaller area, you have a bigger flow rate.
Yeah.
So it sort of reduces the section. So
It's super fun in railway tunnels when the train occupies half of your section. It makes a really interesting dynamic. Okay, guys, this is it. I was told that you want a question.
I had a question now.
Ah,
You focus mainly on the TNO curve in this
Yeah.
presentation. How do you feel? Do you feel that TNO curve, the residual risk included in it, is acceptable? Given, for example, that the French curve reaches a peak of 12 megawatts, and in the BRE studies which you mentioned earlier, I believe they reached 16 megawatts.
they reached the point at which they were extinguishing the.
Yeah.
So I like the TNO curve because it has this plateau. It gives you ability to assess at different heat release rates. Some curves like Joyer curve would be like, it's super straight up, and then you lose the ability to investigate the middle thing. Is it representative for all fires? I'm not sure. It reaches 6 megawatts for a single vehicle, whereas British would go 4. So it still has some higher peaks than you would normally expect. So difficult to say. However, we did not really observe that tremendous differences if you go 8 or 9 or 10 or 12 megawatts. The differences there were not that giant, like obviously worse, but not like, okay, this one works and this one does not completely. It was like a decrease in performance. So I think a lot is in how you understand your margins of safety and how you understand how comfortable you are with risk. I am personally quite comfortable with the TNO curve, especially that my competitors would go with like flat 1 megawatt fire. So I'm bringing something much, much more severe in my calculations. Is it sufficient for a car park fire? I don't know, I hope. Yeah, the British curve, they would be great, but it's, I really think the impact of their calorimeter on the test was severe. It was like really, really small confined space. The Joyer curves, it was done for another, it was done to demonstrate that if vehicles can destroy an unprotected steel structure. So they were purposefully designing a fire scenario in order to quantify the worst threat to the structure. So it was not just a simple free burn of vehicle in a car park.
We typically only use them when we're assessing
For structure, if structural integrity would be my goal, I would probably go with GIS curves because they're the worst documented ones. So for my scrutiny, I would probably go there. But here, in TNO curve, you kind of blindly assume that 18 minutes you have firefighters on your site, because otherwise it would grow and grow and grow. There's a reason why it stops growing, and that reason is firefighters. So we also investigate like first 15, 20 minutes of the fire with that curve and assess, is at this point any chance that firefighters can enter, or it's really already lost car park. So that's the purpose of it. So if you want to.
The problem with the TNO curve is it's designed for a car park with fire detection and fire suppression after 20 minutes. And when there's a fire in a car park without detection, then the fire department says, oh look, there's more than 3 cars on fire.
Okay, I see.
It's a design fire for a purpose.
I understand, and that purpose is very close to our reality of design. So we have smoke detection, we have fire departments. We would consider that as elements in our study. This is why we find it a comfortable thing and better than alpha T squared fire, for example. So it has its own dynamic. I mean, that's like every design fire. It's not a real fire, it's a design fire, exactly. Okay, thank you very much for this. I also have a podcast on fire called The Fire Science Show, and I've had like 3 or 4 episodes about car parks, talking with really smart people, much smarter than me, on batteries. I had Mike Spearpoint on design fires. That's a really cool one. So if you want to check it out, you're very welcome. Fire Science Show. I didn't put the name here, but yeah, you can find it in the internet. So thank you very much, and see you around, guys. Oh.